My report will be devoted to some maybe not so mathematical, more mechanical questions, but I hope some pieces of mathematics will be definitely presented. So I think it's more or less close to the topic of the conference. This work was done with me and Professor Leonid Zubov, and we a short outline of my presentation is presented here. A few words about motivation, then some description of a model we will use, then what continuous distribution of dislocation means and how we can treat them and how we can solve the problem related to this area, several examples, and conclusion. First of all, about motivation. Of course, shells are very well-known element of constructions, and you see the huge difference in size. Of course, people start to do some calculations with the shell theory, starting from these big elements like construction elements or machinery elements and so on. But during to the development of both industry and our science, the application of shell theory goes, and maybe it was a bit strange, from huge object to very, very small object. And nowadays, the shell theory has a lot of application to the micro world, or such object as nano object, or shells of virus, so-called capsids. And you see some pictures at this slide. So first word in my topic is shell. So this is some motivation why we are interested in shell mechanics. Next, how to say, keywords in my presentation is defects. And here some short introduction into the crystal defect theory. First, okay, physical. I say about mathematics a bit later. You see several examples that was imaginary, of course, work. Consider a cylinder. Then you cut a cylinder along its axis, and then move the edge of this cut as a solid bodies. We can move them. We can organize so-called translational movement, and then join the cuts and get some other object. And this situation in cylinder is called translational dislocation or simply dislocation. Or we can rotate this edge, and in this case we call the situation disclination. As I said, Vita Volterra was one of the first who studied such effects in cylinder. I don't know why he studied this, because from the constructional point of view, it has no any sense. But from a mathematical point of view, it was rather interesting problem. And later, Love solved this problem from mechanical point of view. And after that, it was in 1930s. And since then, these defects are called Love distortion or later dislocation. Approximately in 1940s, physicists trying to explain the big difference in theoretical prediction of strength of material and real experimental observation of this strength. And the difference was 3 orders. So 1000 was the difference between the theoretical prediction of the strength of some object and the strength that this object shows us in the real experiment. And they introduce the idea that crystal lattice is not ideal and it has some defects. And they show, or they propose the idea that these defects are more or less close to this structure we can see here. And they use the solutions from elasticity theory obtained by Love, use them maybe not so correctly from mathematical point of view, but fortunately the results leads to the very nice comparison between observation and theoretical prediction. Unfortunately, in the Soviet Union, the dislocation theory was forbidden maybe for 20 years from It was introduced, as I said, in the early 1940s in European literature. In Russia or in Soviet Union, it appears only in 1960s because it was formulated: if you can't see it, you can't propose that it exists. It was a rather strict Soviet approach to that dislocation theory. Forbid it because we can't see it. Only after appearance of the electronic microscope system, that when dislocation or some defects in crystal structure was really observed, only then in the Soviet Union also that investigation were allowed it to organize. Nowadays, the defects are again attract a lot of attention due to that so well-known two-dimensional materials like graphene and so on. So nowadays technologies, industrial technologies of production of such object leads to defect appearance, and they are more or less can be described by these simple ideas like Volterra dislocation. So in our case, we will study two-dimensional system. As I said before, shell is one of the objects of our interest. Shell with dislocation, shell with defects. First of all, what we understand under the term shell. According to our approach, the shell, first of all, is some two-dimensional object, two-dimensional manifold in three-dimensional space. What I should say now, first of all, first idea that it is, of course, two-dimensional object in three-dimensional Euclidean space, but later it maybe not belong to Euclidean space, but in some sense it's something two-dimensional and that exists in three dimension. As I said, our model is not so simple because we want to make this theory more or less close to that previous slide, to that picture. You see shell consisting of, I don't see the, here. You see, this is virus shell, several points, and this is a shell. So this is some sense how to include both point or like ball structure and at the same time solid mechanics. So we use so-called micropolar elastic shell theory. That means that every point has two characteristics. First of all, it has its radius vector. It can be don't see. I see R is radius vector, so we have three coordinates in three-dimensional space of every point. At the same time, every point behaves as a solid ball, so it has its own rotation degrees of freedom, and the rotation can be described by a proper orthogonal tensor or 3×3 matrix. That matrix, and this matrix, what is important, is independent upon R. Of course, when we deform the shell, of course, our particles rotate, but also they can rotate in some sense independently from that main deformation of a body. So we have so-called macro deformation, and at the same time we have ability to micro rotation of our particles. And some notation is presented here. So sigma is the shell surface, r small is radius vector of a particle in the non-deformed state of our shell. Sigma capital is a deformed shell. R capital and H capital are the characteristic of our point of the shell. These are equations of our micropolar elastic shell theory. So we introduce several tensors, or we can think about them as 3×3 matrix. This is in some sense, first of all, two-dimensional theory, because every position of every so every point can be characterized by two coordinates on the surface, but at the same time this is three-dimensional theory because every point exists in three-dimensional space. So shell distortion tensor, this is gradient of radius vector. Usually in nonlinear mechanics it's called deformation gradient. Later I'll show you why we don't use this deformation gradient term, but use shell distortion tensor. Strain measure, this is a characteristic that shows us what happens exactly the strain, and bending strain tensor that reflects the bending deformation and inner rotation of a particle of our shell. Constitutive relation means the relation between the stresses that arise in our shell and the applied strain state. Equilibrium equation is presented here, and we will use, when I say these are some numerical result, I will limit ourselves these specific constitutive relations. They are not very general, but at least they can take into account a lot of nonlinear effects. You see, in some sense, it is quasi-linear equation, but that actually tensors presented here, tensors U, tensor G, are nonlinear function of strain. So this is nonlinear constitutive relations. So now we want to introduce defects in this theory, and the idea to introduce defect is following, is more or less traditional. The scheme is following. We assume that we know the distribution of distortion tensor F inside the shell. Then the question is, what is the displacement? What is the radius vector of a point if I know strain state of our shell? Of course, as I said, if I know radius vector, I can calculate gradient and find strain state. Inverse problem is I know strain state, I know F, and I want to calculate radius vector. Of course, it's just simple integration scheme, and the compatibility equation can give us the uniqueness of the determination of our capital function in the single valued, in the single connected region. What if we go to the multi-connected region? Of course, in multi-connected region, due to that hole, we have multi-valued function. What is interesting, we can prove the following theorem. It's not formulated as theorem, excuse me, because as I said, my mechanical background says me don't say theorem in your presentation. But this is really a theorem that if this F capital field is given, then in the multi-connected region, if I make this cut that transform this multi-connected region into the single connected region, the values of my function on the two edges of this cut will be related with this function. You see, displacement on the plus cut is not the same as displacement of the minus cut. The difference is constant vector. This vector can be calculated as some integral. And this vector is called Burger's vector of a dislocation, and this characterizes one defect in one area. If I have a lot of dislocation, as I said, in real life, the density of dislocation is very huge. What if we want to go from one dislocation to the big number of dislocation? Of course, we can, if in case of n isolated dislocation, we can change sum of integrals by the integral of sum. Fortunately, this is summation operation, and we can do it. Then we can change this contour integral by the surface integral using divergence theorem, and then introduce this parameter alpha and say, it is not equal to 0. Then means that alpha, we can call it dislocation density. If it is 0, of course, we have, for example, non-dislocation case or case of single-valued region, but now we have a single connected area with dislocation density. What it means? It means now that f is not gradient of some function. Now f satisfies not compatibility equation, by vice versa, incompatibility equation. What we have now, okay, we have the previous set of equations. We have extra incompatibility equation. We can formulate some variational principles and even can try, and we are trying to do it now, construct some weak solutions and numerical schemes for investigation of such problems. But to prove that our numerical schemes will work well, first of all, we need to design some, how to say, reference solution, some analytical solution for such problem, maybe not trivial analytical solution, to check then how our numerical schemes correspond or not correspond to that analytical solution. So I show one such solution for spherical shell. We use spherical coordinates here, and we assume that our dislocation density function, alpha, is rather simple. It's some constant proportional to, you see, ER, vector of radius vector, unit vector in the direction of radius. Again, this is not, how to say, example from physics. This example was chosen so in such a way that we can provide analytical or more or less analytical solution of this problem, then to compare this with some numerical results, because without that reference solution it's not easy to verify numerical results. So you see, we choose, if we suppose that this dislocation density is given by the function alpha, then we can seek the solution in the form of spherical asymmetric fields, and then all our equations reduces very step by step. It's technical, more or less, not so easy, but technical procedure, reduce actually from differential equation in partial differential equation actually to the system of two algebraic equations, not so simple, because if I substitute, you see this system is presented here, if I substitute or represent the expression from D1, G1 and so on terms in terms of unknown F1 and F, the formulas will be rather big, but it is just algebraic equation, and we can solve them and get some numerical results. So now we have analytical solution, and we can compare our numerical scheme with this analytical solution. What is interesting in this solution, as I said, in this case, in some sense, because we have our F tensor is not gradient, so in some sense there is no the surface of a shell, but where there is no surface of a shell in our Euclidean space. In some sense, we embed our shell or transform our shell in some non-Euclidean space of curvature and so on. But anyway, we can, what is important for us from mechanical point of view, we can calculate strains and we can calculate stresses, so we can define what happens with this shell during these operations. Short comments for this first slide. I show you another example of problem. First of all, we design a rather general theory of continuously distributed dislocations. Actually, we design some numerical scheme. We will not, we have not checked it yet, so I will not, how to say a few words about the result of this numerical scheme. We have some problem with visualization. I hope somehow it will be overcome. But we find several partial examples. I show one from spherical shell. We have similar example for cylindrical shell, where we have more or less analytical solution. The solution then requires only solving some non-partial derivative, even not ordinary derivative, ordinary differential equation, but simple algebraic, maybe not so simple, but algebraic equations. And again, one interesting problem: what if I want to reflect somehow the real field of dislocation density or dislocation structure we see in real life? Then the question is how to choose that alpha function to provide the structure of the surface we see in real physical experiment. Of course, it's another interesting inverse problem. We are thinking about it, but we don't know how to solve it now. Maybe in a year I can show you some results. And another example of that general theory, or maybe not example, I said about dislocation, meaning translational dislocation. If I want to generalize this theory to the case of rotational dislocation or disclination, we have another problem, big problem. In the case of finite deformation, finite strain, in this case, in previous case, vector r was a multi-valued function. In the case of rotational defect, tensor h that corresponds to the inner rotation of our particle is also multi-valued function. And that means in this case we should formulate the problem in the following way. We have two measures, E and L. They considered as given function, and now our goal is to find vector r and tensor h. Trying to solve this problem, this scheme is approximately the same. The scheme of provement of all theorems is approximately the same. We try to find r and h first of all in single connected region and then go to the multi-connected region. In the single connected region we get these compatibility equations, now two compatibility equations. When we go to the case of multi-connected region, we again make a cut and they have this formula to relating how that plus and minus values of function are connected. What we have here, you see, we have multiplication on some tensor, we call it Frank tensor, but this is about rotation. In the case of finite rotation, unfortunately, finite rotations are not commutative. So if B vector is just summation, so we can assume that if I have n dislocation, I can sum all the vectors and get the total vector Burgers. Unfortunately, if I have several disclinations, I can't just to multiply their Frank tensors, because I have to take into account the order of multiplication. The result depends upon order. This is why, fortunately, in linear elasticity, if I assume that my rotation are small, I'll get the they commutate. In the case of nonlinear, in nonlinear case, in the case of finite rotations, they are not commutative. So we have a big problem that generalizing this theory, the, how to say, more or less mechanical idea, not so mathematical, is just to say, okay, I have two zeros. In the previous case, when I have a compatibility equation, I just change the zero by some dislocation density. Okay, we can do in the same way, say this is disclination density, this is dislocation density instead of two zeros. But what we get as a result, up to now we don't know. There, we have some, how to say, we have to have the same result after linearization. So we have to have the same result with linear theory. But now this work is under the progress. And again, some example. So this is why we concentrate not on distributed disclination, but on one single disclination in the sphere. Consider this is a problem of the following style. We cut a sector of a sphere, or vice versa. We cut the sphere and include that sector into the sphere. The angle of, we have one parameter of a deformation here, parameter kappa. This parameter kappa is related with the angle of inserting or extracting the portion of a sphere material. Then after extraction, or then the cut of the edge should be connected, And this is semi-inverse representation. We assumed that the deformation will have this form. This is such an assumption that semi-inverse method usually this kind of guess. If we guess right, then we can solve equations. If we guess not right, we can't solve equations. Another assumption should we make about H tensor, and in this case we assume that this H tensor consists of two orthogonal transformations. First, some rotation omega of z is unknown function, some rotation of a particle, and then some orthogonal transformation. After some calculations, this case, unfortunately, we can't get an analytical solution with that reduces to algebraic equation, but fortunately not PDE, but now we have ordinary system of ordinary differential equation. It, again, not so simple. This is simple formulas, but if I try to extend it really in terms of that unknown function R, Z capital, R capital, and omega, then it will take approximately 4 pages. But again, this is ordinary differential equation, boundary value problem for that equation. It can be solved analytically, and the results is presented here. So we have originally ideal sphere. If we cut some material, this is, for example, green and blue line, then our sphere becomes have such form. If we add some materials, we have another form, and there is some comparison with linear and non-linear situation. And one last comment and last slide of my presentation will be devoted to one interesting fact. As I said on the first slide, when I introduced the concept of disclination, I show you some cylinder, somebody cut it, and then rotate the edges. Very strange, but in our biology, in our body, we have the object with this disclination. Every artery of human body, or not human, of every body, actually every artery contains the disclination. If we took, how to say, if somebody took somebody's area, artery, and cut it, it actually opened. That means that some, how to say, when artery developed, some disclination was originally presented in this object. And I want to show you this picture of some virus, and you see the picture that shows us that maybe, I don't know, maybe if we can such devices that cut this virus and we see that really it has the same disclination as our artery, maybe, because, excuse me, this picture is very close to the shell with disclination. I don't know. I have no ability to cut the virus and so on, but this rather close. People from physics use the last picture, use the so-called, you see the surface with constant mean curvature. Why such curvature? Because some energy consideration dictates them to choose the surface with constant mean curvature. They choose the surface that more or less similar to that virus. My proposal is to use this, again, excuse me, this solution to model this virus. Maybe it will be more precise. Thank you very much for your attention. If you have any questions.